Hello students, I welcome you in today's session of physics. As you can see here, this is the chapter number 16 of your optics, and this chapter we are going to discuss about lenses. In our previous lecture, we had covered out most of the topics of this refraction of light at spherical surfaces lenses. I hope you know it very well. Now today's we will going to discuss here lenses. This is the topic we have to cover out for today's class, lens. Clear? So I hope you know very well what is lenses. There are two kinds of lenses, basically concave and convex. Fine. So we will discuss about a lens is a transparent medium like glass bounded by two curved surfaces. Fine. It is written here, or one curved and one plane surfaces. It might be possible that the one surface of a lens is curved and one is plane. Fine. The curved surfaces may be spherical, cylindrical or paraboloidal. Fine. You can see here it is written that your surface of the curved surface of lenses might be spherical, cylindrical or paraboloidal, but most of the surfaces are spherical. So the transparent material of the lens is mostly homogeneous, but it may be heterogeneous as well. Now what the mean of the homogeneous and heterogeneous is here? Means the transparent material, it might be possibility that the first material is of the same kind in nature, then you can say it is a homogeneous, and it also possible that the one surface of the curved surface of the lens is of one material and the other surface is of other material. So we can say it as a heterogeneous. So lenses are of two types, you can see here, the lens which are thicker in the middle and thinner at the edges, fine, are called convex lenses. So you have to know very well which is concave and which one is convex. So if you see the lens at the middle is thicker and thinner at the very ends of the edges are known as convex lenses. On the other hand, the lenses which are thinner in the middle and thicker at the edges are known as concave lenses. Fine. Both type of lenses are further classified as follow. Now we further divide in these lenses concave and convex into these categories. The first one is convexo-convex, or you can also write it biconvex or double convex lens. Fine. What happen in these lenses? It's both the surfaces are convex. You can see here in the figure given below, this is the figure 3. In this figure, this one, the radius curvature of these surfaces may be equal or different. The first one is the figure number A of 3A, you can see here, this is convexo-convex, or you can also write it as biconvex or double convex. What happens in these lenses? It's both the surfaces are convex. The radius of the curvature of these surfaces may be equal or different. The second one, you can see here the figure number B of 3B, this lens is called Plano Convex. What happen in this lenses? Its one surface is plane and the other one is convex. Fine. Now come to the third one. The third one is the Concavo Convex, or you can also say it convex meniscus. Its one surface is concave and the other is convex in nature. Clear? The radii of curvature of these surfaces are different. You can see here in concavo convex, the radius of the curvature of both the surfaces are totally different. It is thicker in the middle. Fine. Now come to the concavo concave or biconcave or double concave. You can also see these are the three figures of convex lens. You can see here, and the remaining 3 are for the concave. Clear? So the fourth one we are talking about here, concavo concave or biconcave or double concave. So what happened in this? It's both the surfaces are concave. You can see in the figure number, this is the figure 4 and this one is A. So in figure 4A, the radii of curvature of these surfaces may be equal or might be different. Clear? The fifth one is plano concave. Its one surface is plane and the other is concave. Fine. Its one surface is plane, and you can see here in the figure number B here, the first surface is plane and the other is concave. The sixth one is convexo concave or concave meniscus. So here you can see it's one surface. Meniscus means a curved surface. You are seeing the here in the figure number C, this is the curved surface. So this is called the meniscus over here. So what happened in convexo concave, its one surface is convex and the other is concave. Clear? The radii of curvature of these surfaces are different in concave convex lens here. It is thinner in the middle. The line joining the center of curvature of the surface of the lens is called the principal axis of the lens. A line with joining the center of curvature of both the surfaces of the lens. We called him as principal axis of the lens. I hope it is clear for you. Now we will move to the next topic, which is converging and diverging action of lenses. Fine, you can see here this is the topic 5. Fine. Here we are going to discuss this topic. So what happened? We can consider a lens made up of large number of different small angle prism. So clear? In a convex lens, the base of each of this prism is toward the principal axis of the lens. Figure 5a, you can see the figure number 5 given below here. These are the figures. So what you can see here, this is the figure A and this one is the figure 5b. Clear? Now we will move to upward. So you can see in the figure 5a, while in concave lens it is away from the principal axis. Fine. We know that a light ray passing through a prism is deviated toward the base of the prism. This deviation of light ray increases as the angle of the prism increases. Hence, the ray falling on a convex lens after refraction at both the surfaces of prism bends towards the principal axis of the lens. Fine. Now, greater the distance of prism from the principal axis, greater is its angle and greater is the deviation. Collect at point 5 in figure 5a, you can see this. Thus, the action of a convex lens is to collect the light ray at 1 after refraction at both the surfaces of this lens. What is the action of convex lens? Is to collect the light ray at one point. Hence, this lens is called the converging lens. Fine. Here you can see the action of the converging and this diverging property. This one convex and this one is a concave lens. So, on the other hand, the ray falling on a concave lens after refraction at both the surfaces of the lens become separated. You can see in the figure 5b here, this is the figure of which lens? Concave lens. Clear beta? This one. Thus, a concave lens produces spreading in light rays, hence is called the diverging lens. I hope you understand it very well. The concave is also called a diverging lens and the convex is called as a converging lens, because you can see here in the figure 5a, all the rays of light after incident on the lens point at a certain point. You can see here, this is the point where all the rays are meeting. So, it converges the light ray at a certain point. This is called the converging property. Fine. And what is here? You can see here in the figure B, this is concave lens. It shows the diverging property here. The thickness of a lens is measured by the length of the principal axis between the two surfaces of the lens. If the thickness of the lens is negligible in comparison to the radii of curvature of the curved surfaces, then the lens is called a thin lens. In this chapter, by lens we mean a thin lens. Clear? Here we whatever we study about the thin lenses, we means to study about the thin lenses. Now, here are some definitions related to the lenses. We have to know very well what are the definitions, because in previous chapters or classes we read this definition. Now, what is the optical center? The first one is optical center. So, if a ray of light is incident on a lens such that after refraction through the lens the emergent ray is parallel to the incident ray, then the point at which the refracted ray intersects or appear to intersect the principal axis is called the optical center. So, what is optical center? Suppose a ray of light is incident on a lens, clear, and after refraction through the lens the emergent ray, means the rays coming out from the lens is parallel to the incident ray. Then the point at which the refracted ray intersect or appears to intersect the principal axis is known as the optical center of the lens. The optical center of lens is divides the thickness of the lens in the ratio of the radii of curvature of the surfaces of the lens. Suppose for the first surface of the lens, the pole P1, center of curvature C1 and the radii of curvature R1, and for the second surface the pole P2, center of curvature C2 and the radii of curvature is R2. If C be the optical center of the lens, then we can write here Cp1 by Cp2 is equals to R1 by R2. Fine. Here you can see the intersection in the figure number, this is for convex and this is for concave, you can see here. Since in biconvex and biconcave lenses R1 and R2 are the opposite sides relative to the optical center C is your center of curvature, therefore Cp1 and Cp2 are also on opposite sides. In other words, the optical center of the lenses is inside the lenses. If the radii of curvature of both the surfaces of the lenses are equal, means R1 equals to R2, then you can write here Cp1 is equals to how much? Cp2. That is, the middle point of the lenses is also called the optical center of the lenses, you can see here. For the rays passing through the optical center of the lens, the incident and the emergent ray are parallel, but there is a lateral displacement between them, and this displacement decreases the thickness of the lens, decreases and is negligible in a thin lenses. We consider a very negligible we considering a thin lenses. Hence, ray passing through the optical center of a thin lens goes straight way without any deviation or displacement. This is figure number 7A and 7B in figure, you can see here. This is the above figure here. This is the figure we are talking about. Principal axis, a ray of length passing through the optical center goes straight, whether it is in a concave or convex lens. I hope you understand it. In plano convex or plano concave, one surface is plane. You can see here in the figure number 8A and 8B. This is the plano convex lenses, concave and convex. One surface you can see here is plane whose radius of curvature is infinite. If we assume that in plano convex or plano concave lens the first surface is plane, then R1 is equals to how much? The radius of curvature is infinite. So, we can write here Cp 1 upon Cp2 is equals to R1 by R2, and in place of R1 we can write here infinite. So, what we get here? Cp2 is equals to 0. That is, the optical center of these lenses is situated at the pole of the curved surface of lenses. So, if we ask any question where the optical center of the plano convex lenses situated, so you have to answer that the optical center of these lenses of plano convex lenses is situated at the pole of the curved surfaces. Here you can see this easily, you can, the poles optical center is situated at the pole P1 or whether it is P2, clear. In concave, convexo-concave lenses, R1 and R2 are on the same side. Here you can see this is the concavo-convex and this is one your convexo-concave. R1 and R2 are on the same side of the lenses, therefore, in them Cp1 and Cp2 will also be on the same side of the optical center. Fine. Clearly, in these lenses the optical center will be outside the lens. Fine. Since the radius of curvature, that is P2 C2 and is equals to R2 of the more curved surfaces is less than the radius of curvature P1 C1, that is your R equals to R1 of the lenses. Curved surfaces, therefore, according to the formula Cp1 by Cp2 is equals to R1 by R2. The optical center C will be nearer to the more curved surfaces. Fine. 9A and 9B you can see here in these figures. To locate the position of C, that is center of curvature, C1A and C2A are drawn from the center of curvature C1 and C2 of the two surfaces up to the corresponding surfaces. Now, the line joining A1 and A2 is extended. The point where the extended line cuts the principal axis is the position of the optical center of the lenses. Fine. Now, the second one is the focus and focal length. Here you can see focus and focal length. The rays starting from a fixed point on the principal axis of a lens or appearing to go towards a fixed point on the axis after refraction through the lens become parallel to the principal axis. Fine. This point is called the first focus. Here you can see the focal plane focus in this figure here. and this is the focal point. So you can say that the rays is starting from a fixed point on the principal axis of a lens or appearing to go towards a fixed point on the axis. So after refraction through the lens become parallel to the principal axis. So this point is called the first focus of the lens. In figure number 10, you can see here A and B are the two figures given. The point F dash is the first focus, this one is the first focus, clear, of the lens. In a convex lens the ray starting from F dash, and in a concave lens the ray appearing to go towards F dash. Here you can see emerges from the lens parallel to the principal axis. The distance of the first focus from the optical center of the lens is called the first focal length. You can see here the distance of the first focus from the optical center of the lens is known as first focal length. The lens in the figure 10A and B, the distance CF dash is the first focal length F dash of the lens. I hope you understand it. So that's all for the today's class, student. Remaining topic we will cover out in our next lecture. Till that, do study. Thank you class. Thank you very much.